Today I'm going to talk about Monacella, which is a object relational database that we built at AdStage internally on top of Cassandra. So I'm going to go through a little bit of sort of why we built it and then the mechanisms by which it works. So to give you a little bit of the origin story of it, we need to import a lot of data from multiple ad networks. And just to, I didn't put like this is us, right? So we basically have, ad data coming in from lots of different networks. And we need to pull all that data in and then put it into a unified place where we can then process it and manage it all together. So in order to import all of this ad network data, we have a highly parallelized ETL pipeline. And this ETL pipeline brings in two kinds of data, right? One kind of data it brings in we're not going to worry about here today, which is like ad performance data. So this is data like how many clicks an ad had, how many impressions it had, conversions, and so on. That data is like important and interesting, and we actually spent a lot of time building an application on top of Cassandra that works with all of it. But what I actually want to talk to you today is about the other kind of data that we bring in, which is the metadata that's on the ads. So this is data on the ads that tells you about, say, like what's the name of the ad, or what's the budget, or the targeting criteria. And also how it relates to other entities that exist within that ad network. Because you typically don't just have ads. You have ads that belong to ad campaigns, right? And then maybe there are keywords associated with it and other objects. So you quickly end up in a situation where you have a relatively complex relational data to deal with. And as I said, we have highly parallelized ETL pipeline. That was an architectural choice we made early on because it worked very well for the performance data. However, as we started to scale, this happened really when we were still in alpha. We had very few customers, and we were already hitting connection limits with our Postgres instance that we were trying to store this data into. And if you used Postgres like sort of at the limits, you know that a single Postgres instance can handle about 500 connections, and getting more than that out of it is pretty difficult, right? You can do some tuning, you can build a pretty large instance, pull things off, but we're hitting against that limit. So we had to decide what we were going to do. One option was we could have sharded our Postgres and gone some sort of like multi-tenancy route or federation, basically taking the traditional route of, we have more stuff that we can handle in a single Postgres instance. But in this case, we decided instead to use Cassandra. We weren't quite sure how it was going to work out, but because we were already using Cassandra extensively for all the performance data, we had a lot of experience with it operationally and in terms of like data modeling. We use it additionally for storing a lot of analytics data related to our own conversion tracking. So, we have our own pixel that our customers can install on their ads that allows them to help track, did like clicking on this ad result in conversion, on your website. So given those things and the fact that at the time, so this was about a little bit over a year ago, it was July of last year that we were trying to decide what to do with this, that we were really hitting these limits hard and we knew that we had to solve this problem. We didn't have a whole lot of operations experience within the company or anyone that really would be a good use of their time to be heavily dedicated to operations. So we wanted to build something that would primarily put the complexity in the application layer and not at the operational layer, right? So that's another thing is, we had all had experience working in environments where we had sharded Postgres. We knew how much operational overhead was involved in that. And by comparison, we knew how relatively easy it was to manage a Cassandra cluster. So given that, we said, OK, let's give this a try, see if we can build something that works well enough for us with this data, which is what led to the original version of Monacella, which looks something like this. So it didn't really have a whole lot of stuff in it, right? It basically, and even today, it still has a relatively simple architecture. Most of the heavy lifting is done at the application layer. So the data is stored in a fairly simple way, as you can see. Each column family is partitioned by a primary key, which uniquely identifies the entity being involved. In this case, I'm showing you an add table, but there's ones for multiple things. I listed up here that we have like ads, campaigns, and accounts, because those are the biggest things that we typically deal with in the ad world, right? You have ads belong to campaigns belong to accounts, and you have this hierarchical structure. And that's partly why we thought we could get away with doing something relational-like in Cassandra, because our data is very hierarchical. For at least most of the relationships we care about are hierarchical relationships. And some of that is expressed in the way that we decided to store the data. So you can see here on an ad, and I'll talk about the ad ID in a moment, we also would store in the row things like what its parent IDs are. So there's no need to have some additional lookup step, right? It's just, oh, I know who my parents are. If I need one of my parents, I can go get them. The ID for the ad stores a relatively rich amount of information in it about what the thing is. This way, this serves a couple of purposes. One, we actually already had this ID format that we were using in a few different places in the app. And another, it allows us to store some type information that will, that's very useful to us when we want to actually work with the data later. So here you can see that basically we're storing things like, oh, I know what network it is, I know what type of thing it is, and then it has some unique identifier that is at least unique scope to the type. And then finally at the end, there's this map that just stores a whole bunch of key value pairs that are arbitrary metadata that an entity may have. And the reason we constructed it like that and didn't want to put very much schema information into Cassandra was because one of the problems we have, and this was a big problem when we were storing the data in Postgres, is essentially everything had to have its own table. And that's because every ad network, even though they all have ads and campaigns and accounts and budgets and keywords and things like that, they all have the same kind of things, but they all look slightly different, right? So they all have some common things, right? Like ads pretty much all have a cost per click, but maybe not, right? Because it depends on the kind of ad it is. So maybe it's cost per million impressions or something. They have headlines, right? But maybe not, because say it's Twitter. Twitter ads don't really have headlines, right? They just have the content of the post. So because we had this data that was, these things are very similar in types. We operate on them in very similar ways in the application, but the data is, different enough to cause complications for us. We couldn't just store it all on one table. So, being able to use a map and go schemaless on that stuff was extremely helpful to us. Now, there is some, I should say that as part of Monacella, it does actually have a concept of applying data schemas, but that happens at the application level, not at not in Cassandra. And that gives us more flexibility to decide what we want to do with it. A lot of that comes down to like how we want to serialize the data and things like that. So now, initially when we built this thing, I built it using secondary indexes. Because almost as soon as, because when I built this, we looked through the application. We said, OK, 90% of the stuff we do, right, does not require us to go basically down the hierarchy, right? Oh. So like if I have a campaign, is it going to come back? There it goes. If I have a campaign, I very rarely want to get all the ads in it. So he said, OK, great. That'll make this kind of use case very easy because although it's somewhat normalized in that ads are stored in different partitions than campaigns and different partitions than accounts, I'm going to be fairly limited in how many queries I have to execute to actually get this stuff back. But then it turned out that, yeah, we actually had to worry about that other 10% of the time when we did want to go the other way. Because we tried to re-engineer the way some things were built, and we just realized, OK, there's not a way to escape these queries. We have to do them. So initially, we tried to do that using secondary indexes. If you've ever tried to use secondary indexes, you know that they're kind of weird. They work as advertised, right? Like you will eventually get back the stuff from your secondary index. But if the fan out is too high, they suffer significant performance problems. What is too high? The Cassandra documentation is not very clear on this. I would say too high is basically if your fan out is higher than 5,000, right? Basically, past that point, your stored filter will reach a state where it now will start taking exponentially longer and longer to return as you add items to it. So secondary indexes are not great because of that. And if you get into this situation with secondary indexes, there's nothing you can do to tune a secondary index, right? You're just stuck with it. So given that we were having this problem with secondary indexes and we had built this thing, but we needed to somehow deal with this like 10% of the time where we needed to go in the other direction, we did what many people do, which is we get rid of secondary indexes and build indexes ourselves. So this ended up being pretty handy because at the same time, we also had an even smaller chunk of queries that we needed to run where we actually needed to not only retrieve like multiple items, like say I had a campaign and needed to retrieve multiple ads, there were a few cases where I needed to retrieve all of these, say, like ads with an active status, right? So typically on the ad network, ads have different statuses. Some of them are running, some of them are paused. And sometimes we would need to retrieve those things back. And so we had this mechanism that would allow us to basically tackle both of these problems. Replace secondary indexes with something that would work better for us and deal with this problem of basically having arbitrary queries. And the way we do that is by pre-computing these things, right? So a stored filter is essentially just a pre-computed index, inverted index, that we've generate while at the application layer as we insert the data. We basically make it so that it's part of the right path. So in order to get any data into Cassandra, it has to go through this chunk of application code, and it manages making sure that stored filters get updated. Their structure is pretty simple. It's just an inverted index, right? So it has like this facet ID. That's to identify what thing your data is faceted by. If your campaign's going to ads, then your facet ID is campaigns. Filter name, that's to be able to store some additional metadata just about what this filter is, right? If I'm storing a filter on campaigns and I'm going to ads, I should probably have a name that reminds me that oh yeah, this is the one for ads, right? Or if it's for active ads, yeah, it'll remind me it's the one for active ads. And then I can look it up that way. And then it also has a shard ID. And this is a thing that actually is very useful in your application, like just in general in Cassandra data modeling, if you care a lot about response time. So one of the issues with wide rows is that when you have a row that exceeds about like somewhere in the neighborhood of like 2 to 5 megabytes, that's about all that Cassandra can return to you in a single like request. If it's longer than that, what it has to do is go back, scan, grab more, scan, grab more, scan, grab more. And depending on your access patterns, this can become, extremely prohibitive, especially if you don't get it all at once. So, or if you try to like page through it, it can just take forever to like run over the length of your entire row. And I mean that relatively, right? If your primary concern is throughput, it's fine, right? You can have very wide rows, work with them just fine, throughput will be fine. However, response times will not be great. So to get around this, what you can do is basically internally shard your data at the application layer. And so we do this by inserting just a shard ID into the primary key. In our deployment, there's 32 shards. So it basically just takes the other stuff and then calculates modulo 32 on it and assigns it a shard ID. Oh, I'm sorry, I said that wrong. It's storing this entity ID. So it basically like modulo 32 is that entity ID, chooses a shard, puts it in that one. And what that allows us to do is, OK, fine, now we have 32 of these rows. But now these rows are distributed around the cluster. I can query for all of them at once. And although the total amount of work the cluster has to do is more, I get a much better response time by breaking up that work. So this is one thing you can do to like improve response times if you care a lot about reads and you have a lot of stuff to read back. And then the final part of it is it just stores, we call it this entity ID. It's just whatever the thing is that you're looking up for in this inverted index. In this case, they're stored as the clustering column. I really don't know why I decided to do that. I think it was 3 a.m., and I just decided that that was OK. It really should have been a set type, because if you use set types instead of clustering columns to try to build like a set in your row, you get a lot of advantages. Set types function as CRDTs. At least they do now, right? So you'll get a lot better like write throughput. When you do it this way, you have potential issues with the way that like the rows get written. And it can basically cost more when you're doing like compactions, or if you have a lot of writes to the same row. It can slow down because of the different mechanism by which it writes the row. So that was basically our sensible architecture, and this is actually what's in place today. And once we built this thing, we didn't actually at first really know what we had. We were still sort of thinking like, well, I guess this is some like NoSQL thing that we built, right? I thought, well, it kind of looks like maybe a graph thing. But if you look at most graph databases, they actually can't handle data like what we have, because most graph data, well, essentially all graph databases that I've worked with operate efficiently when you have relatively low fan out. If you have a fan out from like one object to another that's on the order of like millions, they kind of fall apart, right? Because in many cases, what graph databases do is they will try to store adjacent vertices on the same row, right? So they can read them all in very quickly, which is fine for executing graph algorithms, but it doesn't work very well if you care about rapidly like looking at all of the things that are adjacent to something, especially if the fan out is very high. So I guess it wasn't really quite a graph database. And oh, did I skipped a slide. I'm sorry about that. OK, that's the slide I was talking about. All right. But realized, oh, what we actually have are each one of the partitions, right, is essentially an object with some kind of type or class assigned to it. We have type-based relationships between the objects, and we have support for object relationships, but not arbitrary joins. So then I realized, oh, I've just accidentally reinvented an object relational database. Now, why would we want this, right? Because the thing is, almost nobody uses object relational databases, right? Like, almost nobody has ever used them. They are like strictly inferior to relational databases almost always, right? And the reason for that is because they just offer a like more limited feature set than what you could do in a relational database. So yeah, why would we even want this, right? Well, the reason might be you need horizontal scalability, but you don't really need all the features of a relational database, and you need object relationships. So the difference here being that typically in a relational database, you're able to do arbitrary joins between data. If it's expressible in relational algebra, you can do that in your relational database. It doesn't matter how complex your SQL query is, how deeply nested the joins are, you can do it whatever you want. Here, however, that's not possible, but in most applications, you don't need to do that, or it's not necessary to do that if you structure your data correctly. So in some cases, you have to do a lot of deep joins just because your data is highly normalized. Here, by treating the data as objects, or as attributes of objects, you're able to keep the data model relatively simple, and this sort of thing becomes possible. All right, so I made this object relational database. Now what are we doing with it? Well, so I actually hoped that by this time I would actually have Monacella in a state where I could open source it and just say, OK, here's the repo. You guys come check it out. Unfortunately, we're also a startup and trying to make money, right? So I sometimes have to do other things. But this is basically the roadmap for Monacella of what needs to happen before it's sort of like ready for GA. One thing is to simplify the data model. Right now, the data model is highly like the internal data model, in Cassandra. It's actually fairly tightly tied to our domain model. That's because originally we were expecting to use, well, as you saw, we use the stored, the secondary indexes and stuff. And that stuff basically requires that you build new tables for each type in order for it to make sense. In reality, we don't actually need anything that complicated. I showed you two tables on two slides. The object table and the stored filters. That's essentially all the tables you need to implement this thing, right? There's a couple of ancillary tables related to things like paging and stuff like that, but we're not, I don't count those. So the data model needs to be simplified so that way it can be easily used by anyone else, and you don't have to do a lot of weird configuration stuff or really understand deeply how the whole thing functions in order to be able to use it. Stored filter optimizations. This is by far, obviously, the slowest part of this design. Not surprisingly, because we're doing exactly the sort of thing you're not supposed to do with Cassandra, right? We have not fully denormalized the data, and then we get something back, and then when we go to execute one of these stored filter queries, what we have to do is, OK, we go to the database, we get back the stored filter, we get this inverted index, right? It gives us a whole bunch of IDs for objects, and now I say, oh, I would really like those objects. So now I issue to Cassandra 10,000, 100,000 queries asking for all those partitions back. I can't issue all of them at once. My cluster's not big enough, right? And even if it were, that's still a lot of stuff to have to gather together, ship back across the wire to the database. Especially since in many cases, we don't actually need to ship all the data all the way over to the application, but we're forced to because most of the the logic for how this works currently lives at the application level. So we have made some improvements to the way stored filters work, and the plan would be to make some additional optimizations around that, primarily by moving a lot of this logic much closer to Cassandra. And one option might even be to operate within the same JVM. So this is not like unheard of. People have written applications that basically are built so that they run inside the same JVM as Cassandra, and this eliminates a lot of the back and forth that goes on when you're doing network operations. It won't totally eliminate it because we'll still have situations where you have data on other nodes and you have to go retrieve it, but it will cut out as much as it can. And finally, another option that we might try is to actually change the data store. So if you noticed, I didn't really do anything that took much advantage of the big table features of Cassandra, right? Because remember, like Cassandra is really like two things merged together, right? It's big table and Dynamo. So I'm using lots of the Dynamo features for scalability and ease of operations, but almost none of the big table features. So it would be very easy for me to move to essentially anything else that can function as a key value store, but also operates under the Dynamo paradigm so I can get the operational advantages. So one thing I've looked at and haven't fully finished validating is Netflix released a thing called Dynamite, which essentially allows you to build a Dynamo database on top of any other underlying data store. So a couple of compelling options would be to try Redis, maybe as an underlying data store for this, because we care a lot about latency in our application. Or actually using Postgres as the data store in each one of the shards. And then being able to do say some shard local stuff in Postgres before we actually move up to the application layer. Another thing that's available that I should mention is Datastore. So Datastore is essentially the same thing as what we built, except it's actually available today to you guys. So this is a thing out of Dell's professional services arm, and they open sourced it, so you can find it on GitHub. I think it's just I think they're Dell OSS, and then it's Datastore, right? This does very much the same thing that Monacella does, except it's already available to you. It comes in two parts, Spider and OLAP. The Spider part is essentially the same thing as what we built. It uses slightly different technology than we did. However, it also supports a lot more functionality than we do because they have needed other things than we have, right? Monacella is primarily restricted by, right now, what I've needed it for. And as I said, it also has an OLAP layer, which is interesting to us too, because that's also something we built. So, if you're thinking about dealing with have an OLAP application and you're trying to figure out, okay, how am I going to store all my data and all this? This actually provides a fairly straightforward way to manage it. And then finally, another option that we could go back to is actually sharded Postgres. Because a big part of the reason we didn't go sharded Postgres originally is because at the time, a year ago, the state of sharded Postgres was not really that great for us, right, operationally speaking. However, the story has started to change a little bit in the last year. There's this PG shard extension now that automates a lot of the sharding logic that you would have to do as part of sharding Postgres, in terms of making sure your data ends up on the right shard, moving it around, all of that. So that's also another possibility, is that we might reconsider that. That obviously has some operational downsides, right? Sharded Postgres does not have some of the great features that a Dynamo-style database does, like Cassandra, right? It doesn't have the awesome operational features of, reliability, not really having downtime. But, it offers some other things back in exchange. So that's really all I have to tell you about Monacella. So thank you all for coming and listening. And if you have any questions, I'll be happy to take them. I see I've got a heckler already.
I'll be nice. How do you think user-defined functions in 2.2 could help the stored filters problem?
Oh, yeah.
And user-defined aggregation as well.
Yeah. I'm actually very excited about both of those things. So at the time I put together the slides, I guess I hadn't really looked at like what was coming in 2.2 and 3. Or maybe it wasn't announced. I don't know. I never know if I'm just not paying attention or if it's not been announced. But yeah, I'm excited about that and materialized views. Both of those things would actually simplify a lot of stuff that we're currently doing and would attack a lot of performance bottlenecks that we currently have that exist around making like round trips between the application and the database in order to perform operations. Anyone else? No? All right. Well, thank you all very much for coming, and enjoy the rest of your day.